Good afternoon. My name is Larry Nuss, and I am honored to speak to you today at the first Chopra Symposium. And I'm going to present past academic and reclamation contributions that affected current day structural analysis of concrete dams. Here's an outline of the presentation. I'd like to give a brief introduction to the Bureau of Reclamation for those of you who aren't familiar with reclamation. I'd like to discuss some of the contributions that were made during the Hoover Dam design, and then the transition from trial load method of analysis to finite elements, and then recognitions of the compressible water and foundation mass, the importance of field testing, numerical validations, and calibration, and then as I see it, the future direction, and I'd like to list some notable work in the concrete dam analysis. The Bureau of Reclamation manages about 371 high and significant hazard dams and dikes in the western 17 states of the United States. Reclamation was formed in 1902 to reclaim desert lands for irrigation and municipal use. It's currently the 10th largest utility company in the country and the 5th largest in the western United States. Of the 371 dams at Reclamation, about 70 are concrete dams. They range from the highest Hoover Dam at 726 feet to one of the smaller dams, Warm Springs Dam, and we have thin arch dams, Mar Point Dam at 465 feet. So there's a wide range of concrete dams at Reclamation. Pathfinder Dam was the first dam built at Reclamation in 1909. It was 214 feet high, a relatively thin arch dam made with granite blocks built by stonemasons. And it was analyzed by the trial load method. That was a method that was theorized by Dr. Kirchhoff, who lived between 1824 and 1887. And so that method consists of arch elements and cantilever elements, and you vary the load on each until the displacements match up at the intersection points. And this dam was analyzed with dead load, reservoir, and temperature loads. Just to give an idea of the era, in the lower left figure is a 22 horse-drawn wagon team hauling cement 45 miles from Casper, Wyoming to the site. And in the upper right, we see the hired stonemasons from the recently completed Cheeseman Dam in Denver, Colorado. So stonemasons were actually building the concrete dams at that time. A few years later, in Cody, Wyoming, Reclamation built Buffalo Bill Dam. Now, Buffalo Bill Cody was a famous cowboy in western United States, and he actually lobbied Congress for the dam. It's different than Pathfinder because it has mass concrete. You can see the stones, plumb stones that they place along the lift lines. There are no contraction joints from abutment to abutment, and it has the identical shape or design as Pathfinder. So at that time you could see a lot of dams that designs were shared between site to site. This shows over the years Reclamation averaged about one concrete dam per year. And you can see the light green dots here from 1905 to 2000. The light green dots are thin arches. They're actually thin arches that were built in the 1920s. Then there's a long period of time where they weren't built, and then in the 1970s they started back up. Now let's skip ahead to Oahe Dam in 1932 that was built in southeast Oregon near Boise, Idaho. This dam was actually the prelude to Hoover. It was the world's highest dam at the time at 417 feet. By this time the trial load method had matured. They were doing temperature studies at this dam and experimenting with how to place cooling coils in the dam. So this was considered the test dam for Hoover, as I'll explain in the next slide. So at Oahe, they were experimenting with how to put in cooling coils in the dam. And so they placed cooling coils along the vertical contraction joints. and you can see the result. They had a lot of cracking. But in the upper right part of this picture, they experimented with putting cooling coils on every lift line at every 5-foot elevation. And you can see that that section of the dam came out great. And so that's what was done at Hoover Dam. Hoover Dam was the next dam. It was almost twice as high as any previous concrete dam had ever been built. Completed in 1935 along the Arizona-Nevada border, and its sheer size necessitated innovations and advances. And reclamation really became renowned for its expertise of dam building after it built Hoover Dam. During the design of Hoover Dam, there were significant contributions to the analysis of concrete dams. Dr. Westergaard was actually an advisor to the Bureau of Reclamation during the design of Hoover Dam, and he published these papers on concrete dams, deformations of cantilevers and arch dams at abutments, change of stresses in concrete dams due to water pressures in pores, stresses during earthquakes, principles of analysis of arch dams by the trial loads, hydrostatic analogy for arches, and of course his famous paper, Water Pressures on Dams During Earthquakes. And arguably this is the most referenced paper of all time for concrete dams. The largest concrete dam ever built needed laboratory testing. So there were large and small scale testing done at the reclamation laboratories in Colorado, the University of California in Berkeley, University of Colorado in Boulder, and the University of Illinois in Urbana. They studied 2D and 3D models of stress and deformation, cement and concrete investigations, temperature studies and control, and construction techniques. So a lot of these techniques became the world standard then and even now, today. You can see by this model, a very large model of a section through the dam. You can see by the roof line above the model just how large this was. And their goal was to calibrate the trial load method with these large tests. Physical models of the canyon deformations were performed because engineers were worried about canyon spreading due to the tremendous water load. And all these studies fed back into the trial load method for calibration. This very large arch model of an individual horizontal arch looked at the stresses and the cracking at the dam to foundation contact. And in the trial load method, they were actually doing nonlinear analysis by cracking the arches and the cantilevers in the analysis. Rubber and plaster models of the dam looked at strains due to gravity load and water loads. The results were contoured by hand, and as a result from the design and the analysis, there were over 18,000 drawings produced for Hoover. So let's skip ahead 35 years. So in that amount of time, the trial load method had evolved. Instead of just displacements at the intersection between the arches and the cantilevers, people were looking at the radial and tangential twists. More cantilevers and arches were possible, and the work was done by a team of engineers using tables and adding machines. So the amount of time it took to do the trial load calculations took quite long. At that time, the computer was coming out, and so the trial load method was being converted to the computer. And this was being done at Reclamation by Merlin Copeland, Howard Boggs, Glenn Tarbox, Larry Von Thune, and Bob Main. And now the trial load method using the arch dam stress analysis system reduced from months to minutes. At about the same time, the fine element methods were evolving and coming out and being used for concrete dams. And Reclamation started using SAP4, developed by Ed Wilson, Klaus Bada, and Fred Peterson. And also we started using Adina, which was developed by Klaus Bada when he went to MIT. And at that time, so Reclamation did numerous comparisons between the trial load method and SAP4 because the trial load method was very well calibrated with model tests. And we also used SAP4 was the first seismic response history analysis performed for Auburn Dam. In 1976, Reclamation started its Safety Evaluation of Existing Dams program. The goal was to evaluate the hydrologic and seismic stability of all the concrete dams. And to do that, perform a SAP4 or ADINA linear final analysis of each dam, dynamically do the response history using a 3-component ground motion, 2 horizontals and 1 vertical. The maximum model ended up being about 3,000 nodes due to computer storage limits. Use a massless foundation, use homogeneous dams and foundations, no contraction joints, and used Westgard's added mass for the hydrodynamic interaction. That was pretty much standard practice at the time. And we're supposed to use existing material properties. At that time, we would take the static modulus of concrete and scale it up by 50% for the dynamic. We would scale down the foundation modulus by 60% based on the rock quality. We would use either 5 or 10% viscous damping, and we'd used Jerome Rayfield's tensile strength of concrete to judge the strength of the concrete. And arguably, this is the second most referenced paper concerning concrete dams. Hoover Dam was one of the last dams to be analyzed in the SEED program. Reclamation, we just didn't feel that there'd be any stability issues for Hoover statically or dynamically. But the interesting thing was that the Mead Slope Fault is only a mile away from the dam. And the popular SAP4 analysis with massless foundation and Westergaard's added mass showed that accelerations of over 6G could occur at the crest of the dam. Very high tensile stresses of 2,200 psi tensile stress in the dam body. A crack was actually predicted through the dam at about 100 feet below the crest, and large forces into the abutments induced rock block sliding. So this just did not seem credible to reclamation engineers. As we saw it, there were a couple things that were causing the problems at Hoover. One, its height. Second, there were 2 rock formations in the abutments that were causing differential forces into the foundation. And then in plan view, you can see a change in geometry in the upper right figure that caused a concentration of stress. And then the geometry, the downstream slope changes in curvature, which focuses stress. As a result, Reclamation hired a board of consultants that consisted of Ray Clough, Bruce Bolt, and Skip Hendren. And the board recommended perform laboratory testing to obtain concrete and foundation properties, do a detailed analysis of the seismic hazards of the Mead Slope Fault, do geologic investigations of the abutment joint orientations, and also try Anil Chopra's new EACD 3D96 program, linear fine element program. It incorporates mass in the foundation, and the concrete modulus was 3 times higher than the foundation modulus at Hoover. It incorporates incompressible and compressible water. It incorporates reservoir bottom reflection coefficient, and it uses dam and foundation material hysteretic damping. The EACD results were astounding. There are substantially reduced stresses in the dam. The dam was predicted not to crack through, and the abutments were more stable because the force into the abutments was less. As you can see by the figures on the right, with massless foundation, we got 2,200 psi tensile stress, and with foundation mass and interaction, we got 758 psi tensions. So Reclamation had a dilemma. What method should we base our dam safety decision on? So Reclamation decided to perform another analysis and bracket the solution with a dynamic nonlinear analysis to judge the dam stability if it did crack through using the standard massless foundation and Westergaard added mass. So we selected program ANACAP that was developed by Joe Rashid at Anatech in San Diego. It used a smeared crack model for concrete and other brittle materials. So what we did, we pre-cracked the dam in the radial direction to simulate vertical contraction joints, and then we allowed the concrete to crack in any direction it wanted to. And the results showed that the dam would crack at about 100 feet below the crest. The crack that formed was not horizontal, but it was curved, similar to what had happened at Koina. And so the section was more stable above that. As a result, the top of the dam only moved 6 inches along the 100-foot thick section. And so we judged Hoover to be satisfactorily stable given the EACD 3D 96 analysis and the ANACAP results. Now let's look at Morro Point Dam in Colorado. It was the first doubly curved thin arch dam in the United States. It's 465 feet high and only 12 foot thick at the crest. It was designed by Howard Boggs and Merlin Copen after Merlin Copen visited Europe for 10 weeks and learned how the Europeans were designing their thin arches. Dynamic analysis of Morro Point Dam with massless foundation and Westergaard's added mass computed very high tensile stresses of about 2100 psi. Analysis with EACD with foundation mass, compressible water, reservoir bottom reflection coefficient of 0.55, and a modulus of concrete to foundation ratio of about 7:1 computed tensile stresses of about 400 psi. So we hired another board of consultants, John Hall and Dick Goodman, and the board recommended using EACD and calibrate the concrete and foundation properties to the eccentric mass shaker tests that were previously performed by Z. Duran, and then also measure the reservoir bottom reflection coefficient and have Yusuf Ganat do that. So here's the EACD model of Morro Point. It's a substructure approach where you have different models for different parts. The calibration studies at Morro Point showed that we were using the wrong material properties when using mass in the foundation, and we're actually over damping the response of the dam. So we found out that EACD could match the shaker test very well if we used correct material properties. So the standard practices we revisited. So we don't necessarily factor the concrete modulus up dynamically or scale it up between static and dynamic, and we don't scale down the foundation modulus automatically. And it appeared like the reservoir bottom reflection coefficient should be about 0.8, and from that point on, high-risk dams at reclamation were calibrated to field vibration tests. Here are response amplitude plots for before and after calibration. You can see on the top graph, the green is the measured response of Morro Point Dam by Z. Duran, and the red is the computed response. And you see the curve is much lower, the red curve is much lower than the green curve. In the bottom, when we calibrated the material properties, the response was much closer. So let's skip ahead 20 years. And what are we using today in finite element analysis? So we're adding nonlinearities now. We can do contraction joints, model unbonded lift lines, foundation continuities. We're modeling reservoir fluid with fluid elements. We can put in complex geometries like spillways. We can use foundation mass, and we're putting in non-reflective boundaries at the extents of the models. So let's review past contributions. There are substantial analysis topics that were studied and addressed. The trial load method of analysis greatly advanced the 3D analysis of concrete dams, and computers in the 60s increased the speed of analysis from months to minutes. Then the advent of the linear finite element methods. The hydrodynamic interaction was studied, the dam foundation interaction with mass in the foundation, non-reflective boundaries with perfectly matched layers, and now complex advanced commercial finite element codes permit nonlinearity such as contraction joints, cracking, and foundation discontinuities. So let's look at current studies, future direction, and needs. So there's always a need for research funding, and this is being pursued by Robert Hall. Using perfectly matched layers that was developed in Elsteina by Ushnisht Basu, and applying that in production mode is being pursued by Osmar Pinner. And then applying ground motions in any commercial finite element software is being pursued by Anil Chopra and Arnshel Loke. And of course, calibration and validation of analysis models is vital, especially with the highly advanced finite element programs we're now using. So Z-Dron is pursuing performance-based testing. A large-scale shake table tests are being pursued by Mark Schultz. I think more and more people are pursuing field testing. And then we need back analysis of historically shaken concrete dams and see if our analysis match what was measured in the field. And then there's a lot more collaboration with engineers in the dams industry, and we're sharing more and more information amongst ourselves. And then identify and understand the uncertainties in finite elements and material properties is being pursued by Mohammed Amin Hari and Jerzy Solomon and Yusuf Ganat. And then, of course, a lot of different agencies and companies are going to risk-based and probabilistic methods, and we'll probably all be working with that. So let's look at the direct finite element method that's being worked on by Anil Chopra and Arnshel Loke. And this method includes all the important factors being considered currently for concrete dams: mass in the foundation, compressibility of water, reservoir bottom reflection coefficient, radiation damping, spatially varying ground motions, and nonlinear mechanisms. The direct finite element method is a way to correctly specify seismic input. The standard practice has been to have an earthquake motion specified at a single control point on the foundation surface. But the direct finite element method requires the seismic input to be specified as spatially varying effective earthquake forces at the model boundaries. This is a schematic showing the easy to implement procedure that Arnshel is developing to apply the effective earthquake forces in any commercial finite element code that uses mass in the foundation and non-reflecting boundaries. This shows the work that Osmar Penner is doing at BC Hydro and working with Ushnish Basu at LSTC Livermore on the effective seismic input in 3D when you're using perfectly matched layers. These are some studies by Mohammed Hari at the University of Colorado in Boulder on the performance-based earthquake engineering in concrete dams. And it's basically methods, probabilistic methods that have been developed in the building industry and bringing them to the concrete dams industry. It involves looking at probabilistic distributions of material properties and loads and developing fragility curves, and then bringing new ways to look at the results in concrete dams, say for instance with tornado diagrams or different methods like that. Performance-based testing of concrete dams is being pursued by Z-Dron at Harvey Mudd College. And basically they take a cold gas thruster and it imparts a force into the dam, and they can measure the response at different locations on the dam. Another way is by ambient vibrations naturally occurring in the earth, and you can get natural frequencies, mode shapes, and modal damping estimates. So thank you very much, and I would like to wish my best for Dr. Chopra in his retirement, and thank him and his many students for all their contributions to the field of concrete dam analysis and their friendships over the years. And we'd like to thank all the great engineers that have come before us and paved the way in our concrete dams industry.